Hey, good morning, everyone. Um, welcome to class number 10 of our course on Network Fundamentals for Cloud. Our class is being recorded. I am already sharing my screen and we are good to start. So now that now that we are completely free of the mid-semester exams, I think we can get back to focusing on the post-midsem syllabus. I'll do a quick recap of what we discussed in the last class so that you can all remember when it's been a break of a week in between. So we'll all recollect together what we discussed last time and then we'll pick it up from there. So let me just put it on slideshow. So if you recollect, what we were discussing last time was the modern architecture, the topology for the leaf spine for the modern data center network. And we said the class network topology, and within the class network topology, the one of the most basic class topology, which is also called the leaf spine topology, is one of the most often used topology in modern data center networks. So while this may seem a little simple in terms of the topology itself, this acts as a building block. Right? The same topology, because it's an architecture built for scale out, it can be easily extended to increase both the capacity as well as the computational power in the data center network. So we saw that the class network topology consists of a layer of switches called the leaf switches, which are also sometimes called the top of rack switches, which exist within every rack. Okay? And that rack, apart from the leaf switch, also holds the other servers. Okay? So all these servers are connected via the leaf switch to each other. The servers in one rack are also connected to servers in the other rack via a backbone network, which we call as the spine. Okay? So spine is a same set of switches which connects to the leaf switches and thereby enable connectivity between servers across multiple racks. Okay? So it's kind of a mesh architecture between leaf and spine switches, where the leaf and spine switches need not be of different types. They can all be of the same type of switches. Okay. So this is what we had discussed, and we also talked about the benefits of this leaf spine topology, where we noted that one of the biggest benefit comes from the use of homogeneous equipment. It's easier for a data center network administrator and infrastructure manager to be able to manage a homogeneous set of equipment rather than having to deal with multiple different types of equipment as existed in the access aggregation core architecture. We also saw that in the leaf spine topology, because the leaf is connected to multiple spines, Hmm? there are actually more than two paths between any two servers in the network, and therefore there is much larger redundancy. That larger redundancy helps improve the blast radius of the data center network, because now if you have a failure in one of the links, it doesn't reduce the capacity as much as what it did in a access aggregation core topology. We also saw that this is a scale out architecture, because when you need more capacity or bandwidth in the backbone of the data center network, you can add more spine uh, uh, switches. So by adding more spine switches, you get more bandwidth between the edges. Whereas if you need more computational power, you want the data center net to do more work, you add servers and leaf switches, which enable you to support higher computational power. Right? So it's a scale out architecture. It's also simple because the functionality is distributed across all nodes in the network. So there is nothing special about the spine switches compared to the leaf switches. All network functions are supported by all network nodes in this data center network. Okay. It's unlike the access aggregation core architecture where aggregation switches had more or a larger role to play. And this also comes from the fact that the data center network in the leaf spine following the leaf spine topology is built with routing as the interconnect model so that layer 3 networking is what drives the modern data center network. Okay. So there's a question which says leaf spine work as routers rather than switch. Shouldn't these be called as routers than switches? So this I think I've clarified in a lot of uh, sessions earlier as well that a lot of times when nodes function both as layer 2 switches, so they forward traffic within the network as layer 2 switches, and when they act also as layer 3 routers, sometimes the terminology used in literature is to call such nodes as L3 switches, layer 3 switches. So let us not get confused by the terminology, whether it's, you're right, I mean, you can call them a router. The general term used in literature is always a switch because these are layer 3 switches, which have the twin function of switching as well as routing inbuilt. So that's what they call it, but you're right. It has all the network functions, the layer 3 routing functions. So you can very much think of it like a router. So what is more important is to understand the functionality. The terminology is a little confusing at times because literature has all these terms. Layer 2 switch, a layer 3 switch, a router, often indicating that a layer 3 switch is a switch which can do both a routing function as well as a switching function at layer 3 and layer 2 respectively. Okay, so that is what we discussed. Okay, let's today now look at the classic class topology. So what we saw in the form of the leaf spine architecture was more of a adaptation of the classic class topology, which was built to cater to telephony network, circuit switch network. The classic class topology is actually a three-stage topology. Right? So in a telephony network, we do understand that there are local exchanges, telephone exchanges, which cater to a particular geographical region, which could be a residential or a commercial area. Right? It's a geographical area. So, and then you have a collection of net switching, telephony switching nodes in between, which connect the local exchanges to each other. So if I just try to draw a very abstract diagram of what a telephony network looks like, I will say, okay, let's say these are telephones, individual telephones which exist at residences or commercial establishment. There's a last mile connectivity, which is directed, typically a twisted copper cable that goes to the local exchange. Then we call such an exchange an LEX or a local exchange, which connects to the which supports the last mile. And then there are many such local exchanges, each catering to their own region, but these local exchanges are then connected to each other via what we call as trunk lines. Okay. And therefore, you create a network of interconnected telephones, and that's how the circuit switch network architecture at an abstract level looks like. Now, the intent of the classic class topology was to create a circuit switch network where any telephone in any part of the network could always be able to create a dedicated circuit or could get resources to a destination telephone all the time, right? So kind of the requirement is to create a always on network where every time that a source telephone tries to call a destination telephone or a telephony number, there's a path that can always be found, right? So there is enough paths in the network, in other words, enough resources and paths in the network to cater to any pair of telephones to get connected in a call. Now, remember when we talked about circuit switch networks, we said it's not just about the availability of a path. In circuit switch networks, the resources across that path are reserved, are pre-reserved for that call even before data transfer can happen. And this is something that the control plane does. So when I dial a telephone number, the control plane protocol not only determines the path to the destination, it also enables reservation of resources, bandwidth across that path. And that is one of the reasons why we call it a circuit, because you have a dedicated resourceful path towards the destination. And therefore, there's never a situation of congestion or lack of bandwidth to carry the data. That's not the case with circuit switch network. So what we need is a network. If I'm saying, okay, I need a network where I'm never out of bandwidth, I can always find a path where there is resources available from one telephone link to the other. How do I build that? And this was the problem at hand, which was solved when the class topology was discovered. Okay, so if you try to look at this class topology, you can look at all these inputs as in the telephony network, nothing but endpoints, the telephones. Okay? And these could be treated as the local exchanges, which are receiving, in this case, every local exchange is receiving n input line from n different telephones. Right? So when you look at the input stage in this diagram and the output stage in this diagram, you can think of all the square boxes in the input stage and output stage as a set of local exchange. And think of the middle stage as some intermediary switches, telephony switches, which are just trying to connect the input stage to the output stage. Okay, so creating a connectivity network between the local exchanges on the input side to the local exchanges on the output side. That's what the middle stage is trying to do. So the way classic class topology looks like is that let's assume that we have T input stage nodes, local exchanges, T output stage nodes or switches, and we have M intermediary middle stage switches that are being used to connect the input stage to the output stage. Every input stage node can take N inputs and can output M outputs. Okay, so essentially we are saying that each input stage node is a N cross M switch. N cross M switch means it can take in N inputs and output the traffic coming from N inputs to one of the M outgoing links. Okay? So in totality, we are saying there are N plus M ports on this switch. Right? So total, you have N plus M ports on the switch. But we say N cross M because it's kind of interconnecting the N inputs to one of the M outputs. Okay? So it's an N cross M switch. We assume that the middle stage is a T cross T switch. So there are T incoming ports, T outgoing ports. And then the output stage is the reverse of the input stage. It's an M cross N. Right? So once again, it can connect to N outputs and can take in M inputs. Now, if you look at it, this kind of a topology that we've created with a 3-stage network, an input stage, and a middle stage, and an output stage. How many inputs in total do I have? If I have T nodes, I have T cross N total telephones on the input stage. Correct? That's T cross N. Now, if you look at the output, once again, I have T output nodes and there are N outputs coming out of each output stage. I can use the output stage to connect to how many telephones towards the end? Once again, T cross N. Okay. So in a way, I'm saying I can create T cross N pairs of calls through this network without facing any congestion. That's what we are trying to do. Right? We have 10 T cross N total inputs, T cross N total outputs, and we are trying to create T cross N pairs of calls between these inputs to outputs by using a middle stage creating a three-stage topology. Okay, so this is what clause topology enables you to do. You will see the reason why this works is because of the redundancy in the network. There are multiple paths through the network, and that is what enables the availability of path between the T cross N pair of nodes. So that's how the clause topology was built. Of course, depending upon how many parallel calls, see, not always T cross N parallel calls will be ongoing. The network is never fully utilized. So that is why the number M, T, T cross T, M cross N, they've been kept as configurable variables in a way. What I can always do is to do something like this. I can do N is equal to M is equal to T, in which case I'm saying, okay, I have sufficient paths in the network to always have the maximum number of T cross N simultaneous calls also ongoing. But because telephony networks are seldom 100% utilized, it's not that all of the T cross N inputs are trying to make calls to T cross N outputs at the same time. I can choose this value of M and the value of T, N, and M in a manner such that I can cater to the utilization that I expect in the network. So let's say I believe that it's always never more than 60% of my users are never simultaneously active. That's the upper limit. I can choose T, N, and M in such a fashion that when 60%, even when 60% of the people are simultaneously trying to make a call, there is always a path through the network. So I can tailor T, N, and M accordingly. But how does this three-stage clause topology translate to what we looked at, the leaf spine? Now, if you think of using, as I just suggested, the value of M, N, and T to be equal. Okay, so let's assume M is equal to N is equal to T. That's the special case of this classic clause topology. It becomes a special case. M and T are variables, but I'm saying, okay, let's make all those three variables equal. So it becomes a special case of the classic clause topology. And now let me flip. Think of it like a book. This is the center of the book. And flip the input stage onto the output stage, or vice versa. Flip the output stage onto the input stage. Okay? You get what we saw as the leaf spine topology. So the middle stage essentially becomes the spine. And the input stage and the output stage switches, when they get flipped, they come on the same side of the spine, they all become leaf switches. Right? Jyoti has something. When N is equal to M equal to T, the clause network becomes symmetric. That's right. Meaning same network of links per stage. That's correct. Right? And then you can see it, even later on, you can try to realize that I'm actually created enough paths in this network such that I can have N into T simultaneous calls ongoing, pair of calls going ongoing. So this is how the classic clause topology translates into a simpler leaf spine. Because in our case, all we have to do is to treat all the input stage nodes as leaf switches, which are top of rack switches. Similarly, these are also top of rack switches. And the middle stage is acting like a spine. It's the backbone, which is connecting the input stage to output stage. In our leaf spine topology, the spine is acting as a backbone connecting all leaf nodes together. And the redundancy exists, right? So every leaf is connected to every spine. That's what we said in the leaf spine topology. Every leaf connects to every other spine. That becomes true when I say M is equal to N is equal to T. I treat the input and output stage as leaf, the middle stage as a spine. The classic clause topology translates into a simpler leaf spine topology. Okay? So this is what we use as a building block in our modern data center. Now, why am I saying building block so much? Okay? Earlier I said we can scale this topology vertically as well as horizontally. I can scale out, which means horizontally. If I have more computational power, I can add one more rack with more switches and a top of rack with more servers and a top of rack switch. And this top of rack switch can connect also to each of the spines. When I need more bandwidth, I can add more spines. If that is always possible, then why do we say it's a building block to modern data center? Well, eventually you will run out of ports, number of ports on this switches. So see, I cannot keep on adding these servers and top of rack switches because let's say I've now exhausted all the ports on both the spines as well as the, or maybe one of these has gotten completely exhausted. Maybe let's say the spine ports have already gotten exhausted. So let's say, hypothetically speaking, let's say it was a 16 port switch. Okay. And we're saying they're all of the same type. So leaf will also be a 16 port switch. Let's say there are 8 servers in a rack. So 8 of those ports have already been used to connect these servers. Remain 8 other ports which I've used to connect to, let's say, 8 spines already. I already have 8 spines. Right? So that's how the leaf switches have been used. Let's say there are also 16 racks already. So all the 16 ports of the spines are also used. Now, if I have to add a 17th rack now to increase further capacity, I can do that. The servers can still connect to the top of rack using the 8 ports. But this top of rack, when it has to go back and connect to all the spines, there is no available port available now on the spine to cater to the 17th leaf node or 17th rack. Right? Because all my ports on the spine have been exhausted. Okay, the reverse is also possible. I may not be able to add more servers into the rack because all ports on the leaf switch may have been exhausted. Okay? So even the leaf spine topology, depending upon the physical number of ports on the leaf and spine switches, eventually there'll be an upper limit to how many servers you can connect using the leaf spine, basic leaf spine topology, which will be limited by the number of ports on these switches. And my intent is not, see, I can always go to market ship for new leaf and spine switch which do not have 16 port but which are 32 port. But that's a waste of my existing infrastructure. Am I going to throw away the 16 ports leaf and spine switches? That's not what we want. Okay? We want an architecture which can build and continue to grow using the leaf spine as a building block. So it's like Lego. You can take Lego blocks, keep on putting them together to keep building bigger and bigger systems. Right? You don't have to throw away the earlier things. So that's where leaf spine topology acts more like a building block. You can use that topology to continue to scale the data center network. Okay, I'll show you a simpler example right now to help you understand. By the end of the class, I will introduce you to the 3 case studies which I had earlier mentioned also. A Google data center case study, a Facebook data center case study, and a general paper, research paper, which talks about how to build scalable and extensible modern data center networks using class topology. So this third one, which I mentioned, is more of a theoretical research paper. How do you do it? The other 2 are practical applications of it in Google and Facebook data center each. I'll show you towards the end of the class Google and Facebook data center network topologies. You see, these are pretty complex, but underneath they are using the leaf spine topology as a building block. Okay, you can break it down to very simpler modular leaf spine topologies getting put together to create a larger network. I'll show you how it's done in a simple example. Okay, so let's start with what did we say? We said it's limited by the number of ports. So what I've done is I've taken a particular type of port, a switch, and saying, let's assume we have 4 port switches only. Okay, that's the upper limit on how many ports I have on every leaf or spine switch. So using the leaf spine architecture that we've discussed so far, this is one topology that I can create. And I want all leaves to be connected to all spines. And I also want some servers to be connected. So how many servers do you think are possible to connect in this topology? This 2-tier class topology using 4 port switches. I actually have 2 spines, 4 leaves. They are connected. you'll see all ports are exhausted. All 4 ports are used. On the spine, 4 ports are used to connect to the 4 leaves. And on the leaf, 2 ports are connected to connect to the spines and 2 are used to connect to server. How many servers have I connect? How many servers do I have in this topology? How many physical servers have I been able to connect using this leaf spine topology with 4 port switches? Come on, it's simple. Am I missing chat? I was getting, yeah. Arup says 8, Jyoti says 8, and Yuvraj says 8. All of you are right. Okay? So I can have, so it's 4 leaves means I have 4 racks, as Yuvraj has mentioned, right? I have 4 racks. All of these leaves are top of rack switches. And because 2 ports of each of these TOR switch has already been used to connect to the 2 spines, I only have 2 ports left on each of them. So I can connect 2 servers. So total, yeah, Jyoti, that calculation is correct. 4 leaves into 2 servers per leaf equal to 8 servers. So 8 servers is the computational power I have in this data center network. And let's say this is sufficient for me to run my business for now. 8 physical servers are sufficient to run my web applications. It cater to my client traffic workload. Now let's say my subscriber base grows and I'm getting more incoming traffic from my clients and I have to meet the service level agreement. I have to ensure the latency is not increased. What do I need? I need more servers. I cannot add more servers in this. My complete capacity is exhausted. But I don't want to throw away S1, S2, L1, L2, L3, L4 as well. 4 port switches is my basic building block. So what is the way to extend it? The way typically that data center network administrators use to extend is, as I said, use this small block as a building block, right? And create more tiers or hierarchies in the network topology so as to grow the number of servers. Now, there are 2 ways I can do this. One way, I'll come to this term later, virtual chassis. Right? This term I'll explain slightly later. Where this name you can try. I mean, why virtual chassis? I'll come to it later. But it's called a virtual chassis based 3-tier class topology using, once again, 4 port switches. So what have I done? I've taken this structure and used it as a building block. Okay, I've repeated it twice. 2 such repetitions of the same topology I've brought in. And then what I did was I got in another 3rd tier of switches. Once again, 4 port switches, made a 3-tier topology. Right? Now, okay, let me explain why I'm calling it a virtual chassis based technology. So what I do is I treat this building block in itself is a scalable topology because it has complete redundancy inside. Right? Every leaf is connected to every other spine. There are multiple paths between any servers. So think of it as one virtual node. Think of the block as one virtual node. Right? And this one virtual node is capable of individually running in isolation on its own. It's like, yeah, as Jyoti has said, you can look at it like a logical grouping of switches such that they create one larger switch, right? So what is it in reality? Right? I can think of it like a virtual switch, a larger virtual switch. Okay? And this virtual switch is actually a very clean switch. It has a switching fabric inside. This is the switching fabric inside the virtual switch. It's a non-blocking, redundant switching fabric inside. Okay, it was able to run in isolation when I had connected servers directly on the leaf ports. Right? The fabric was sufficient to cater to all these 8 servers. So individually, I can think of it like a larger virtual switch, which is capable of handling all the traffic coming on these 1, 2, 3, 4, 5, 6, 7, 8 ports. The inner switching fabric is capable to handle that. So I put them up as two switches now. So think of them like two larger spines. So, okay, let's call it super spine 1 and super spine 2. I've given it a new name. Rather than calling it a spine, I'm calling it a super spine. Why super? Because it's a larger spine, which has multiple smaller switches inside and a switching fabric inside, creating capacity. So I'm calling them two super spines. Now each super spine has how many ports? 8 ports. So in total, by having two super spines, what have I done? I have created 16 ports capability of amongst these two switches. And what I've now done is I've brought in 8 top of rack switches, and instead of calling them L1, L2, just for avoiding confusion, we are calling it T1, T2, T3. So L was the terminology used for leaf. T is the terminology being used now in this new topology as top of rack, because L has gone inside the super spine. So I'm calling the T's as top of rack switches. I can have 8 top of rack switches. I can continue to follow my recommendation of the class topology, which is what? Every leaf should connect to both the spines. Here there are super spines. So I connect T1 to L11 and T1 also to L21. I connect T2 to L11. I connect T2 to L21. T3 I connect to L12 rather than connecting it to L11, because L11 I see 8 ports coming out. So I can use them in any fashion. To connect all leaves with all super spines. Now in this new 3-tier topology, let me erase all that I've written so that you can see it clearly. In this new 3-tier topology, how many servers am I able to connect? How many servers do I have now connected? Have I doubled the capacity by increasing one more level of hierarchy in the network? Right? I have. So now I can double the capacity. From 8 to 16, I could transition by adding one more layer of hierarchy in the network. So the network definitely becomes complex. And while when I by the end of today's class, if time permits, when I show you the Facebook topology, data center network topology, you'll see it's pretty complex. It's actually a hierarchical structure created out of the basic leaf spine topology. But what it helped me was to do was create a new network structure, which is of course more complex than the basic building block. But it is once again a non-blocking. See, the classic class topology was something that was built to have a non-blocking. The term we use is non-blocking network topology. So there's always a path between any pair of nodes. It's a non-blocking topology. That was the intent of the class topology originally. So what have I done? I've once again converted a smaller topology into a more complex topology. But even this, because we are following all class topology rules, we have a new non-blocking network topology, and it follows and has all the benefits of the basic class topology, and I did not have to waste any network resource. I just procured more more switches and extended the topology. So Arup, I'm just coming to that what you asked also. So yes, this is one way that we saw we could extend it. It's not the only way. Different data center networks have different methods to extend. So yes, one way is what you've written. When I introduce one rack with Tor, then the existing rack can become a spine for that rack. This is what we are seeing here. Right? This is what we've done here. Right? We've kind of created a virtual chassis of switches, and therefore we are calling it a virtual chassis based 3-tier topology. This is actually a model which has been popularized by Facebook. Okay, this is what Facebook follows a lot in their data center network, the virtual chassis based network topology. But this is not the only way, and in fact, you can think of other methods to reuse these network switches. See, what I did have to do still was to do some level of recabling. Recabling is required. Why? Because earlier I was directly connecting servers over here. Those servers had to be plugged out and had to be connected here, whereas the leaf switches T1 and T2 now got connected to L11. So some level of recabling is required, but I could reuse the network infrastructure. I did not have to waste that. The other way I can do, if I'm allowed to do recabling, is to do something differently also. Virtual chassis is not the only way to go about doing things. I can follow another architecture which is called a pod based 3-tier class architecture using 4-port switches. Now, what have I done in this is I've elevated S1 and S2 to a third level hierarchy, and I'm now calling them SS. So S1 has become SS1, S2 has become SS2, right? And I have added two more, SS3 and SS4. Okay. Below each of these super spines, I've created a pod structure. What is a pod? A pod is a term that we use for a repetitive structure. Right? It's the same structure that repeats. So I have a pod, which itself is a class topology, a basic class topology of 2 cross 2, 2 leaves, 2 spines, and this is how they are connected. Okay. And then I have, because I have 4 super spines now, I can have 4 such pods. Okay. And every pod eventually allows me to connect. Every leaf in the pod allows me to connect 2 servers each. So each pod has connectivity to 4 servers. Okay. So think of this pod as a leaf switch. So earlier, what did I do? I actually created a virtual chassis as a spine switch. I created a super spine as a combination of switching fabric. Here I've done slightly differently. I've created a leaf, virtual leaf actually. So you can call it a virtual leaf, but the term we use is a pod. Okay. So I've actually extended the leaf switch to actually be a bigger leaf, having not just 2 available ports, but 4 available ports by creating a pod structure. Once again, I needed one more level of hierarchy. I needed 3 level hierarchy to extend. But it's a different way. Rather than making a bigger spine, I've made a bigger leaf. Right? Calling it a pod and differentiating it from the super spine in the earlier by calling that a virtual chassis. So this is another cabling approach, another networking approach by using the same 4-port switches that I can extend the capacity to 16 servers. This is the model that is popularized and used by Microsoft and Amazon. Their data center networks are built using a pod-based architecture. Okay. But irrespective of whether you use virtual chassis or whether you're using pod, one thing that you should, even after this class, when you look at this slide, carefully analyze both these 3-tier architectures. You'll see what we talked about as the requirements of a leaf spine architecture. Every leaf should connect to every spine. Right? So that rule you'll find is met in both these architectures. So it's actually a more complex leaf spine architecture only. So this is how you can scale class topologies. You can grow class topologies, making your networks more and more complex by increasing the capacity in your networks. And that is why class topologies are called a scale out topologies, because you can scale up the network. Okay. Yeah. So as Jyoti said, it's basically some amount of reconfiguration, recabling that you will have to do to scale it up. Yeah. Yeah. Kind of leaf spelling and spine killing. That's correct, right? So this is what you can do to expand your data center network to larger and larger sizes by reusing the existing leaf spine architecture, introducing more hierarchies. Of course, you don't want to always get into recabling, right? Recabling is a big business because when you're doing this reconfiguration and recabling, you are actually for that intermittent period. Of course, you will do it locally, one step at a time. You will not bring down the entire network. You will first locally maybe recable this part, right? Then the next one. So it's not as if the entire network is down all the time, but it is an intrusive activity. It does impact the network operations for some time. What you do is, if I'm Facebook or if I'm Amazon, I will at least estimate the needs on my data center network for the next 5 years. I will plan for a topology which can extend without bringing down the network at least for 5 years. Right? And then, of course, after 5 years, if it goes beyond, I have multiple choices. I can bring down that data center and do something different. Or what we can do is which I'll actually talk about later in this course. Right? So you cannot arbitrarily keep on rescaling, because as Arup has just said, recabling means outage. Right? So after a particular scale of my data center network, outage will not be acceptable. So what do I do then? I start replicating data centers. So once my data center has reached peak capacity, and peak capacity, when I say that, it's not just peak capacity in terms of all switch ports having been used now. It's also physical space. After a while, my data center will be out of physical space. I can't just keep on stuffing in physical racks of servers in the same geographical data center. So once I've exhausted the capacity, physical capacity also of my data center, what is the next step to increase my, what is the next step to that scale out architecture to increase my capacity? Replicate data center. And that is where the topic of multi-site data centers will come in. Why do likes of Google and Microsoft and Amazon have so many data centers all across the globe? Because one, they have to cater to an audience which sits across the globe. Two, eventually every data center will run out of capacity. You have to replicate data centers, create a new data center, create a new data center. So you have to have multi-site data centers which are themselves connected via a backbone of themselves. We'll talk about that later when I reach that point. Okay. Right now, we're just talking about one data center and how you can scale within that data center to increase capacity. Okay. Afterwards, once your data center is completely, exhausted or filled up, then we'll keep on adding data centers. As data center becomes a building block, then I'll add a new data center to add more, support more customers. Okay. So essentially what we saw so far, okay, by looking at the class topology, the simple example of 4-port switches that we took. See, 4-port we saw still after 16 hits a limit. So Google and Microsoft, who know they have a lot of travel, never start with a 4-port switch. They'll probably start with a 48-port switch, so that their expansion capacity is much more than what a 4-port switch will give you. So those are some choices you will make accordingly. I'm saying, when you design a data center network, what are the design choices that you have to make? So topology is definitely a choice which we saw. Traditional data center networks followed access aggregation core topology. The modern ones follow class topology, leaf-spine topology. So choice of topology is definitely a design choice. Oversubscription of bandwidth. What should be the bandwidth of each of these links? That's a design decision. Should it be 100 Mbps each? Should it be 1 gigabit per second each? Should it be 10 gigabit? What is the bandwidth? So this is the cross-section bandwidth. Think of it like the backbone of the internet. Think of all of these as edge nodes in the internet, and this is the core, backbone. These are like tier 1 ISPs. So isn't the data center network kind of replicating the internet architecture? So you can think of it like the backbone. What should be my cross-sectional bandwidth on the core of the internet? That itself is a design choice. You have to estimate the traffic, not just client-server traffic coming into your data center network, but as we learned, 90% of the traffic in a data center network, a modern data center network, is server-server traffic. So what should be the cross-sectional bandwidth on my core is what you have to plan. Do you want to use multipath routing? It's basically what we achieve by introducing, along with the other routing protocols, a new control plane protocol called equal cost multipath. So yes, we do, because this enables us to use multiple redundant paths simultaneously. So if I can add ECMP to the portfolio of routing protocols I'm using in the data center network, I can enable multipath routing as well. Right? So I can simultaneously send my traffic via multiple available paths, unlike OSPF, which will only identify one path through the network to send traffic. If there are multiple equal cost paths, ECMP will help me enable multipath routing. And of course, when I make these choices of topology, how much bandwidth over subscription should I go with, what should I use multipath routing, this is all contributing to your cost of setting up the data center network. So eventually you have some budget at hand. That budget is what is constraining you from making some of these design choices. So data center network design is not a simple task. People who are, I don't know how many of us in this team work in a data center network as network administrators, but if somebody does, you can understand what I'm trying to say. It's a complex job. Designing a data center network is a complex job. There are a lot of aspects that you have to look at under the overall constraint of budgetary cost. Okay, so the case studies thing I'll come to towards the end of today's class. Let me first go to the next topic. I don't go by that contact session numbers. I'll upload later consolidated PPT. Don't worry about that. I mean, I'm using different slide decks, but I'll merge them into a contact session 10 slide and then share it, upload it on the. Okay, so I'm skipping recap because we've done this. Or let me very quickly say, so what have we learned so far? Let me read something that Jyoti has put up on the chat. For an example, with 4-port into 10 gig switches, this pod-based class, 160 gigabit per second is the cross-sectional network bandwidth. That's right. So what is the cross-sectional is what we are talking about. That's right. So thank you, Jyoti, for that example. So summarize, what have we learned from last class until now? I said we will start by looking at the endpoints, where we were in the year 2000. So this is year 2000, where we are in the year 2025. This is what we've talked about. We've talked about what was the traditional network topology in the year 2000, the access aggregation core. Well suited for north-south traffic or client-server traffic, application architecture. Applications were at that time only client-server application, but not suited for the modern applications, which are cluster-based applications where server-server traffic is more. So what do we see in 2025? How have the data center network topologies evolved? They have moved to a net topology invented by Charles Claus called the class topology. The basic building block is the leaf spine. It can be extended to more complex, and there are variants of even the class topology. Leaf spine is one of them that we are covering in this course. If you're interested to read more, you can even look up fat tree topology. It's another variant of the basic class topology that's also extremely popular in data center network. Okay. So this is what we've learned. Now, what am I now going to do in the remainder of today's class is I'm going to trace this journey. From the year 2000 to 2025, it's not as if we jumped from access aggregation core to this topology in one shot. That never happened. Yeah, we all know networks don't suddenly change. They don't jump from one state to another state. They evolve. So what happened between the year 2000 to 2025, from where we started with access aggregation core and ended up with these complicated topologies in the data center? We actually built using leaf spine as the building block. A lot of things that happened in between. And while you may not be interested in these intermediaries today, you should know them. Why? Because it helps you understand what worked and what did not work, or why it did not work. And therefore, it helps you understand network design better. As I said on the previous slide, network design is a complex job. And to understand network design, you need to know what works, what does not work, and why something does not work. So when I trace this journey from 2000 to 2025, how did the technology, how did the net data center network gradually evolve? You'll actually learn this better. This design part of the network topology you'll learn better. Okay. So yeah, I'm skipping this part because we've just done it. I'm going to directly jump to this data center networking technology evolution, the entire evolutionary path. Okay, this is what we are going to talk about. Okay, now this is actually we are at a very logical point, and while we are not yet at our hour boundary, it's only 50 minutes into the class. If you think we take a 5-minute break now rather than 10 minutes later, this is actually a good point to take a break, because once I start with that journey of evolution from year 2000 to 2025, I would actually like to go in one flow so that you see how it's evolving. Yeah, let's take a break now. 5-minute break. It's 11:21 by my watch. I'll start sharp at 11:26. So come back at 11:26 or in 5 minutes by your watch. Okay, I think we can start after the break now. It's 5 minutes. Okay, so our journey in this data center network technology evolutions will start from year 2000, where we learned that the topologies used were actually access aggregation core topology. Right? So access aggregation core is the topology that was designed, and the challenge that we had discussed then was that access aggregation core technologies, which actually used a layer 2 switching method within the access aggregation part of the network, suffered from issues related to broadcast storm. Okay, this is what we had discussed in a couple of class and the previous class we had talked about this. And this broadcast storm, to limit it, the spanning tree protocol was brought in order to mark some of the cyclic paths in the network as redundant paths, as standby links, so that the cycles in the network could be broken and therefore the broadcast storm could be arrested. But because it led to underutilization of the network bandwidth, we said that alternatives were identified which enabled or which suggested creation of VLAN specific spanning using VLAN specific spanning tree protocol, so that different VLANs had their own spanning trees, and in totality, considering all the VLANs, the entire network bandwidth could be utilized. And this was what they created as an intermediary solution to arrest bandwidth underutilization, at the same time avoid broadcast storms. But the last thing that we had then discussed was this itself had some challenges because STP is not a very stable protocol in complex network configurations. So access aggregation core data center network topologies are complex in their own right. And when a lot of under certain extreme conditions where some faults occur in the network, STP is working on resolving it, in between something else changes in the network. Certain cases, STP would land up the network into some very weird kind of configurations where the network would become quite inoperable. So those challenges with STP existed, and till here is what we had discussed earlier. I'm just summarizing what we had discussed in earlier class. So while STP could not completely solve the problem of broadcast storm in access aggregation core topologies, and while people did not want to move away from access aggregation core topology suddenly because there's an existing installed infrastructure of access switches, of port switches, of aggregation switches, I can't do away with all this infrastructure suddenly. The plan to reuse that infrastructure but to do away with the problems of STP was that led to the evolution of a virtual chassis technology. So we've just in a while back we saw what do we mean by the term virtual chassis, and thankfully Jyoti I think had also summarized or provided a definition to it, saying it's a virtual chassis is a term that we use to denote because of the term virtual, right? And chassis is like a group. Right? So by virtual chassis, we mean a logical grouping of many physical switches or network nodes connected together such that they behave as if they are one large switch or one large network node. So virtual chassis was also a technology which was designed to solve the problem of broadcast storm. See, why do you have a broadcast storm? The reason I have a broadcast storm in access aggregation core topology, if I draw it, once again, I don't have the diagram right now in front of me, but you remember this was the access switches, and there was always a pair of aggregation switches, and the way these were connected was access will connect to this, and because it's a layer 2 switch domain, even aggregations connected to each other, what do you have? You have a lot of cyclical paths in this network. A lot of cyclical paths. But if I can club these two aggregation switches together and treat them as a virtual chassis, okay, I think of them like a virtual chassis. Now I don't have to just think, I have to make them work like a virtual chassis, which means if they have to be one switch, both of them cannot run their control planes. Both of them cannot run their switching functions, or they cannot have both running their control planes. So virtual chassis will have data plane functionality in both of the switches, but a single integrated control plane. That is, when you have an integrated control plane, that's only when you can see it as a unified logical device. So if I can club these two aggregation switches and make them work as a virtual chassis, what does this architecture, if I redraw, becomes like? It becomes like one larger aggregation connected to two access switches. Where is the cyclic path in this topology? There is no cyclic path. I've done away with the cyclic path. So in a way, these two links have been clubbed together into a higher bandwidth link. This technology is actually called link aggregation, LAG. Yeah, Arup had given some example, like example, a Nexus switch with VCP, virtual chassis. Okay, and these two links can also be seen as a higher capacity switch using the LAG protocol, link aggregation protocol. So it's eventually like I have double the bandwidth, but connected to a single aggregation switch, which is a virtual chassis. It helps me avoid loop. So even without getting into the challenge of spanning tree protocol or the ensuing complications that result out of it, a virtual chassis technology helps me avoid the cyclic paths in the network without having to reduce the data plane functions. I have double the bandwidth, so the data plane is not impacted. Okay? This is what the virtual chassis technology brought in. Right? So this is what after STP challenges were discovered, the next step in the evolution path was the evolution of the virtual chassis technology. So you can treat virtual chassis technology as also a form of network function virtualization, even though it is not network function like virtualization in the sense that we've discussed it, where we've said NFV is more like creating VNF, virtual network functions, which are software-based implementations of network functions. It's still a N:1 virtualization. You've taken N network nodes and created one virtual node out of it. So that's why the term virtual chassis. Okay, so it implements N:1 virtualization. As I've said, it integrates the control planes of the multiple devices together to form one unified logical device. Okay, so basically the different physical devices share the same control plane. It's equivalent to saying that I've created a cluster of the physical network devices, increasing the capacity, making it a bigger switch. Now, because I'm treating the virtual chassis as a unified device, what all other network architectural changes do I have to bring in? We said any network node is a combination of three planes: the data plane, the control plane, and the management plane. Any network node has these three planes, sorry, MP. We said the data plane is changed because I bring in the protocol of link aggregation, LAG, which merges multiple links to the virtual chassis into a single higher capacity link. Treats it as if it is, these are not two individual links, but one link of higher, double the bandwidth. Right? So that's done using a protocol called link aggregation, LAG. The control plane is changed because I have to have a unified control plane. But I also need to change the management plane, because now this logical device is one virtual chassis. It has to have a unified management IP address. It should appear like a single node to all the external entities, both at layer 2 as well as layer 3. Okay, so I've already mentioned this link aggregation protocol that helps the logical device to merge the multiple different physical links into a single logical link of more capacity. Think it's like dual homing. It avoids the problem of dual homing of terminals, which is what caused the loops in the access aggregation. So we've avoided those loops. What we also need to do in the control plane is to build in a new protocol, because there are two aggregation switches you merged. Right? We want a unified control plane. So the way that it is done, one of the switches becomes the master switch. And the master switch runs the control plane function for the entire aggregated virtual chassis. The standby switch has the control plane function, but it's put onto dormant mode. It doesn't work. But if the master were to fail, the whole benefit of the access aggregation core topology was redundancy. If the master was to fail, the standby aggregation switch should come up as an independent switch with a whole control plane function fully functioning, so that the network can still continue to work at half the capacity. So an additional protocol which requires election of one of the nodes as master and master standby switchover, basically determining when the master node fails so that one of the standby can take over the master role. This protocol is required to be built and operate in the cluster. Virtual chassis technology, therefore, is not a simple extension or evolution. It involves changes in the data plane. It involves changing in the control plane. It does impact the management plane, but it does solve the problem of spanning tree protocol. So a lot of virtual chassis technologies became popular at that time, and in many private data centers which have not evolved till date, they still continue to use virtual chassis technology. You'll find such data center networks spread across the globe which are still not evolved to modern topologies, and they still use virtual chassis technology. So Cisco, VSS, Huawei, CSS, these are virtual chassis technologies that evolved during that period, and some data center networks still practice it. Okay? So this was the first step forward. Avoiding spanning tree protocol challenges, avoiding broadcast storm, the virtual chassis technology was evolved. Now, what are the disadvantages? So I said, yes, a lot of changes are needed in control plane, data plane, management plane to do this, but is that the only issue? Or do you see other disadvantages? This slide is summarizing the disadvantages of the virtual chassis technology. For one, the performance of the virtual chassis itself. Think of the virtual chassis as a switch. Now, while I've been using this phrase, it's a larger switch. In reality, the performance of the switch is not the same as one large switch would have been. From a data plane standpoint, yes, it's a large switch. It's combined the data plane capacity of two individual switches and made a larger switch of double the data plane capacity. But because only one of the nodes is running the control plane, the overall performance of the virtual chassis will be limited by what? The performance of the control plane of the master switch. Because it is the control plane of the master switch which is providing the control plane functions for the entire chassis. So what did we say earlier about the limitation of the access aggregation core architecture? We said the aggregation switch has an overload of also having to handle the ARP traffic, proxy ARP, on behalf of the access switches and the underlying servers. It has to handle all the ARP traffic. So it already has an overload. Now we are saying that instead of two aggregation switches handling the ARP load, the entire load has now come down to one control plane which resides in the master switch. So it's even further increasing the workload on one control plane of one of the aggregation switches, thereby doing what? Limiting the scalability of the data center network. Because if this data center network were to scale, when I say scale, I'm talking in terms of scaling the computational power, adding more servers. Adding more servers will mean adding more access switches. What will happen? ARP traffic will continuously grow. The limitation in the control plane on the virtual chassis will limit this scalability. Okay? So that's one disadvantage of using virtual chassis technology. Second, it does bring down the reliability to some extent. So last slide I said you need a protocol for master election. If the master were to fail, you need a protocol for one of the standbys to become the master. So you need some kind of a protocol running in between the masters and the switches slave for this whole process. Now, this whole protocol is going to take some time. So detection of the master switch failure itself takes some time. You'll build some kind of a heartbeat mechanism. You'll detect the master has gone down. It will take some finite amount of time to detect that. Then the protocol runs where the standbys kind of think of it like an election protocol. They discuss amongst themselves and they say, okay, they agree on one of these standbys to pick up the master role. That takes another finite amount of time. What happens to the virtual chassis during this time? If any network topological changes have happened during this time, or any traffic is coming from outside the network, the aggregation switch or the virtual chassis is not in a position to handle it at that time while all of this is running. So packet loss during this time is unavoidable. Okay, so master switch failures do cause packet losses for an interim period of time until a new control plane switch, until the new standby switch takes over the master role. This reduces the reliability of the network to an extent. Third challenge was more from the perspective of network management. So from a management plane standpoint, the challenge of upgrade. See, we know that any computational node, even a network appliance like a router or a switch, runs a piece of software or a firmware, which often has vulnerabilities which need to be patched, which comes new functionality gets added, so a software upgrade is needed. Now, if you look at a virtual chassis, it's not one node, but many nodes packed together into a chassis system with one control plane and one management interface. When I have to upgrade the nodes within this virtual chassis, right, the procedure is no longer the same procedure as what I used to do with individual nodes. Individual nodes, I would just update the software and make a restart. But now these are multiple nodes working in tandem. I cannot have some of them running a newer version of the software and some running the older version and not have compatibility between those software versions. So what do I have to do? I have to build a new method for software upgrade whereby I have to make sure that all get upgraded to the same software version simultaneously before I restart them to come up with the same software, while at the same time making sure that the interruption to service and the resulting packet loss is kept to a minimum. It's not a simple protocol to build. So management functions like software upgrade and patching, they all undergo change. It all becomes more complicated. Lastly, there is bandwidth waste in a virtual chassis system. So what was virtual chassis? The way I described it, you had two aggregation switches, and earlier these aggregation switches were also connected via a link. And before this link was used for data plane traffic. So an access switch sent some traffic like this. The aggregation switch could pass it like this before it could reach to a core. So it could be used for data plane. Now that they are part of an aggregation virtual chassis, this link is mostly being is of course used for data plane traffic like it was earlier, but this is now also being used for an additional protocol, which is the master selection and the master failure handling protocol. So this link is now having more control plane traffic, and control plane traffic in any network is seen as an overhead. It's seen as a bandwidth waste. So you always try to limit the control plane traffic. So in a virtual chassis system, you've actually ended up increasing the control plane traffic, in a way bringing in more wastage of the network bandwidth. So these are some of the disadvantages that come with the virtual chassis technology. It has some benefits, but it also has disadvantages. Okay. Okay. So I'm actually skipping this slide because I've kind of covered this earlier also, multi-chassis link aggregation technologies, where it's basically an extension to the basic virtual chassis technology. So you use the same core principles of virtual chassis technology, but you also use link aggregation technology to link together multiple chassis together to create a multi-chassis topology. It's a further extension to virtual chassis, but I don't think we need to get into this level of detail. I'm just skipping this slide, avoiding getting into so much detail. But there are vendors in the industry which have these kind of solutions also. Multi-chassis link aggregation. Cisco's VPC is an example. Juniper's MC-Lag multi-chassis link aggregation group. Huawei's M-Lag multi-chassis link. These are extensions of the basic virtual chassis technology, which are called multi-chassis link aggregation topologies. Okay, but I'm not getting into that level of detail because not required so much. The idea you've gotten about what is a multi-chassis technology and how does it solve the challenge of spanning tree and broadcast arm, but it comes in with some disadvantage. The next evolutionary technology, once again in the access aggregation core topologies of the data center network, and this was a major jump or a big jump in terms of the technology as such, was the introduction of a layer 2 multipathing technology, or L2M. Now, they sat down and said, okay, what is the fundamental problem that we are facing in this access aggregation core network topology? The fundamental problem is the broadcast arm. We've tried STP to solve that problem. It has its own challenges. We've already done multi virtual chassis, but it has a lot of disadvantages. Let me ask myself, is the topology bad, or is my choice of network protocols being used in that topology? So what is topology? Topology is nothing but a way of structuring my network. It's a network structure. It's a hierarchical structure. But in the apart from the structure of access, aggregation, and core, the additional decision that I took, which was my choice of protocols to run in this structure. And what was that choice? That choice was, I said, I will run layer 2 protocols in the access aggregation part of the network, and I will use L3 protocols in the aggregation core part of the network. And why? I said I will do that because layer 2 networks are self-configuring, self-learning, they switch very, very fast because of hardware-based switching. Those benefits made me make those choices of the protocols to be used. In reality, there is not so much with the network topology, the structure. It's more a choice of the protocols that I've used to run in different parts of that network structure, which is causing the broadcast storm and actually taking me into this endless loop of trying to solve it by STP and virtual chassis and so on and so forth. But what if I was to relook at those choices I made with respect to my network protocol and say, okay, I decided to use layer 2 switching in the aggregation access part of the network because of the fast switching at layer 2. But self-learning is leading to broadcast. And broadcast is the whole problem here. Can I do away with the self-learning property of the layer 2 switches? Okay. Now, if I have to do away with that, and we know routers don't have a self-learning property, then I need a different way to learn paths in this network, and therefore I need a different way to set up my layer 2 switching tables. So when I discussed self-learning, how it works in one of the earlier classes, I said self-learning switches learn of which node is reachable via which port, and then they keep populating their switching tables. But if I don't want to have self-learning because it relies on broadcast, I need to have something similar to what routers have at layer 3, which is what? A routing protocol. Okay, so this is a very dramatic and a drastic thinking that came in, which said, okay, we know that time immemorial, historically, layer 2 networks have been known to be self-learning networks, which learn and create their switching tables using broadcast mechanisms. And layer 3 networks, because of the virtue that they are larger networks, they're part of the wider area networks, they're part of the internet. They can't use, because they can't use broadcast, they use routing protocol. But if a network cannot use broadcast and it has an alternative to use routing, if I'm facing the same challenge in my layer 2 network now, I don't want to use broadcast in my data center network because it's causing challenges. Can I not also use the same logic and bring in a routing protocol at layer 2? Yes, it is unheard of. Nobody has done it in the past, but what stops it? So that is the basic ideology behind layer 2 multipathing technology. The big principle in L2MP is the introduction of a routing mechanism that you typically see in layer 3 networks into a layer 2 network. That's what they did. They said, I don't need spanning tree protocols. I don't need virtual chassis. My topology access aggregation core is fine. I can live with it. I don't have to buy new switches. I don't have to recable my network. It's fine the way it is currently. The topology is fine. All I need is to change my protocols used in the aggregation access part of my network to also to stop broadcasting and self-learning and start using a routing protocol for populating or learning paths and filling up the switching tables. That is why it is called a, see, multipathing is what we know is a routing approach. You look at multiple paths and you find the best path to use. But when you bring it down to layer 2, this is where the name comes in, layer 2 multipathing technology, L2MP. Now, we've seen that in layer 3 networks, predominantly amongst the distance vector routing protocol and the link state routing protocol, the link state routing protocols are more popular because of the fact that their convergence happens very, very quickly. They converge very fast because every node forms the same topology of the network. And because they all use the same Dijkstra's algorithm, they converge to the same path. The algorithm will run in a deterministic manner. And if all of them have the same view of the topology, then it's going to give the same path to everyone. So its convergence is never in question. So it's highly, the link state routing protocols, we say converge faster. Unlike distance vector, we sometimes take a lot of time to converge. So LTMP technology made the choice of using link state routing protocols at layer 2, which meant that they needed a new identifier to be associated with each node so that each node could be addressable, like an IPv4 kind of an address, right? Which actually is a layer 3 addressing entity. They brought in a similar addressing entity for layer 2. Each node used something similar to a link state routing protocol to first exchange link state advertisements, calculate the network topology, and once the network topology is calculated, then calculate the forwarding database, or in other words, the switching table. This is what L2MP brings in. L2MP is a technology, it's a way of thinking. It's not a protocol. One of the most popular standardized protocols that follow the L2MP ideology is the Trill protocol. Trill is the name of a protocol. It's a standard protocol which follows the L2MP. L2MP is a technology. Trill is the protocol that implements that technology. Okay. So Trill is a standard L2MP protocol. It's standardized by the Internet Engineering Task Force, the consortium which comes out with all internet standards. and it's one of the most popular L2MP protocols. What is Trill? Let's talk a little bit about Trill protocol. Just the basic concepts of what Trill is. It's an acronym which stands for Transparent Interconnection of Lots of Links. That's the name of the protocol, Trill. It is implemented by a new set of devices which are called Trill switches. So earlier I had these access and aggregation switches in the topology, which we were saying were L2 switches, layer 2 switches. But layer 2 switches by definition don't have a routing protocol. Now we are saying we need a new type of switches which is an L2MP switch. It's something, call it L2++. It's something more than layer 2. It's not layer 3 yet, but it's more than layer 2. It has the routing functionality of layer 3 inbuilt. So it's like L2++. We call it, we give it a new name and call it RBs. I am forgetting what was the full form of RB in Trill router. I'm not sure if it was router bridge or something like that. It's like a L2++. Somebody can Google and maybe post it on the chat. I forget what it was, full form of RB was. But it's a new type of a switch. It's a Trill switch called an RB. It has the layer 2 functionality, but on top it has also an additional functionality of link state routing. So it combines the techniques of bridging and routing. It's not a full-fledged layer 3 switch, but it's a layer 2++ switch, an RB. Now, I need a new protocol, which is the which is the link state routing protocol in Trill, whereby I can exchange these link state routing protocol messages. So Trill has its own protocol format. See, the underlying network below Trill is still Ethernet, still the layer 2 network. So Trill actually, this is, let me blow it up. This is how a Trill packet looks like. This is the payload, which is the real data. On top of it, okay, you have, so what you had was an Ethernet frame. Earlier you were transmitting an L2 frame. This was your L2 frame. So earlier I was just sending this layer 2 frame directly on a layer 2 network, which was the access aggregation part of the network. This was my original L2 frame. I don't want to impact that part of my data plane. I just want that my layer 2 frame should be constructed the way it was earlier. But what does Trill do in addition is now Trill adds a new header on top of this. Think of it like your payload, like your data, original data that had to be sent on the layer 2 network. Trill adds its own header on top. Why do I need a Trill header? Because I have to put in the RB's addresses. This packet now has to be routed, not switched. It has to be routed from an outgoing RB to an incoming RB. It's like sending a packet from a router, in source router, to a destination router, source node to it. So I do that by, instead of putting an IP header, I put a Trill header. I have a egress RB nickname. It's like your IP address. Ingress RB nickname. Some other tags. Ether type equal to Trill. So ether type is a field which indicates to Ethernet what is the next level protocol. Earlier, normally we would use ether type. You have done that Wireshark lab. So what did you see ether type carrying? It carried IPv4 or IPv6. It basically mentioned what is the protocol that Ethernet is carrying, ether type. So here it says ether type is Trill. So Trill is the next level protocol carried within the Ethernet header. And now this Trill packet is what is routed from the source to the destination. Okay, so just like IP packets are routed in an IPv4 network, a Trill packet is routed in a Trill network. Okay, and just like you take an IP packet and eventually what did you do when you have to send it over a layer 2 network, you put it into a Ethernet header. A Trill packet is also eventually, when sent, over a layer 2 data link layer, it also will further get encapsulated in a new Ethernet header, an outer Ethernet header before it's sent. But the earlier layer 2 packet is still intact as if it was the complete payload of the Trill header. So the reason why we've done this encapsulation is I don't need any changes on the servers. Now that you've seen the packet format, let me explain why this packet format, why so many encapsulation. These servers are still not these. I don't want these servers to be impacted. What are these servers generating? To the access switches, what are they sending? They are sending L2 frames because they believe it's a layer 2 network. They believe this is a layer 2 network. So they are sending L2 frames to the access switches to switch these frames towards the destination. That is what is this, the inner payload. That is your L2 frame, which the server has generated. But the RB knows that it is no longer an L2 network. What is it? It's a Trill network. So what does the RB do? It takes this L2 frame coming from the server, which is this lower frame, encapsulates it in the Trill header, which is like an IP header. Right? In that it says, I am the source RB. That's where this ingress RB nickname comes in. This is the destination RB. So what have I done? Using routing, I've determined the destination path. Right? And now putting in the destination RB, I forward this packet. So when it gets forwarded, this Trill network also runs on top of layer 2 protocol. Right? It's a complete protocol stack. So it will once again get into an outer Ethernet header and get switched and routed through this network to reach RB3, from where the decapsulation will happen and this original L2 frame will go to the server. So it's like a virtual private network. This is what we do over the internet when we create a VPN. Aren't we doing the same thing? Except for the fact that instead of the Trill header, we have an outer IP header. So it's like creating a tunnel through the Trill network, via the Trill network between two servers. Right? The two servers still get to see the same L2 frames that they earlier saw. But a virtual network has been created between server A, server B, server C. A virtual layer 2 network has been created between them by using tunneling of traffic through the Trill network. And tunneling is typically characterized by encapsulation. New headers are being put in. Okay? So this is what Trill does in an access aggregation core network topology. It uses the layer 2 MP concept, brings in a routing protocol at layer 2, which is a link state protocol, creates new switches called Trill switches, which act like encapsulating endpoints. They take the layer 2 frames from the servers, but rather than just switching them as is through the network, encapsulate them into Trill packets and route those Trill packets through the Trill network to the destination. Okay, this is L2MP. Now, if you understood when we discussed so much about network fundamentals, we talked about VPNs, how VPN is nothing but a tunneling technology. If you've understood all those fundamentals very well, you will have no problem in understanding Trill because the concept is exactly the same. It's like tunneling a layer 2 packet through a higher order Trill network. That's all we are doing over here. But by bringing in routing protocol in the access core, so this was, let me erase some things and then write. So this was your access switch. Access. This is your aggregation switch. This is still your router core. And this is an IP network like it was earlier. So the topology is maintained. I did not do away with the topology, but I extended or patched, software upgraded these switches to make them Trill switches instead of pure L2 switches. Okay, so this is how Trill works. Now L2MP has its advantages, which is that I have done away with the virtual chassis concept, which was a complicated thing in itself. It had a lot of disadvantage. So there's no virtual chassis anymore. Okay? I made it. What have I done in reality? Haven't I brought it a step closer to the modern data center network? Modern data center networks, what do they have in the class topology? They have a class topology and they use L3 routing as the networking protocol within the network. That's what modern data center networks use. I brought it a step forward. I'm using Trill, which is very close to layer 3. It's L2++. It's a step forward towards doing that. But they also still have some disadvantages. The disadvantages, see, by now data center networks are starting to evolve and move towards cloud computing. Cloud computing means I need virtual tenant networks to be created for my tenant. So I am no longer looking at this data center network as if it was a physical network created to connect physical servers. That's true. It is a physical network that connects physical servers. But with virtualization technology coming in, every physical server can have multiple virtual machines. And upon every physical network, I can create multiple virtual networks. And then I can support many tenants. This is the benefit of cloud computing. I can have on the same underlying physical infrastructure multiple tenants with their VMs connected via their virtual networks. So by this time, this concept of cloud computing had already started to come in. I want to support over my data center network multiple tenants with their own virtual machines and virtual networks. L2MP can do this because we still have that concept of VLANs that I can create on top of my layer 2 networks. Trill is still a layer 2 plus plus. It doesn't do away with the layer 2 protocol. So VLAN is still a layer 2 protocol that exists. I can use the VLANs to create virtual networks for different tenants that I have. But it's limited to 4,000 tenants only because VLAN ID is only a 12-bit field. And in VLAN, we use the VLAN ID to distinguish between the different virtual networks. So I'm limited by that field and the number of bits it has. And therefore, in a way, we are saying any data center network that uses the Trill protocol and wishes to support a lot of tenants is still limited by 4,000 tenants. Now, when Trill was designed, they actually knew about this problem, that VLAN only supports 4,000 tenants. They knew that the world is evolving, cloud computing is becoming very popular. At some point in time, they will have to support more than 4,000 tenants on the data center network. This problem was known. In fact, a solution to this tenant problem was also considered when the Trill protocol was being designed. I'll show you the Trill protocol header again. See this options field over here? They reserved 32 bits in the Trill header. Okay? So field of 32 bits was reserved in the Trill header, which they said they will use later. Instead of VLAN ID, they will use this field for tenant identification. That's what the plan was. And we will not use VLAN protocol. Instead, in the Trill header itself, unlike having, where is VLAN ID? VLAN ID is a field in the L2 header. So they said we'll not use it because all our RBs are Trill capable. We will instead use this field in the Trill header to identify the different virtual networks or the tenants. And then I'll be able to support 2 raised to the 32 tenants. I'm doing away with this limitation of 4,000 tenants. So this problem was known. A field was even reserved in the Trill header to use it later for solving the tenant problem. But till date, that problem hasn't been solved. And the reason is not because it cannot be solved, but because Trill itself became outdated. Okay? So by the time we got around that stage where the number of tenants would have gone beyond 4,000 and Trill would have to be extended to, instead of using VLAN, start using the reserved header for tenant identification. Before all those software changes could come in, Trill became outdated as a protocol. Okay? It got replaced by the next evolutionary steps, which we will talk about. Okay? So VLAN is a limitation. Trill does have a field that can be used, but it's not been designed, not been used till date. Okay? The deployment cost definitely got increased with Trill because you needed one, new forwarding identifiers to be assigned to every chip. New forwarding processes. Yes, I can implement it in software. What is it? It's like a routing function, forwarding function. In routers, I implemented. I can do a software patching on my access switches and build in a new forwarding process inside of them. But if I need speed and I need some of these functions to be done in hardware or in network processors, like routers have, then it inevitably requires upgrade of the forwarding chip. I'll have to bring in new ASICs which can do the Trill forwarding or routing, or I need to bring in new kind of network processors which can do the Trill forwarding much faster. So inevitably, if I need speed or performance, I'll have to upgrade the forwarding chips in these existing hardware L2 chip switches. So it'll mean some increased deployment cost. If I want to avoid the deployment cost, then I'll have to take a hit on the performance. I have to implement all of this in software, all these forwarding functions. Third disadvantage of Trill is, see, when we talked about the internet and we talked about the benefits of IP as a networking protocol, we said IP is not a standalone protocol. It comes with a suite of protocols. There are protocols like ICMP, which is a control management protocol that is used in IP networks. Things like echo, traceroute, all of these utilities, they use the ICMP protocol underneath. IP has its own multicast protocol. IP has its own control plane routing protocols, OSPF, RIP, they are all IP-based protocols. So IP comes with its own family or suite of protocols for the control plane, management plane, broadcast, multicast, control and management, ICMP. So it's an exhaustive set of protocols where if you choose to build a network using layer 3 IP protocols, then you have everything available in these standards. But when you design a new protocol like Trill, all the paraphernalia that you need alongside it to handle the operations, administrations, maintenance, all those O&M parts, even a multicast if you have to do in Trill, you need to have new protocols because Trill is not IP. So you need new O&M protocols, new multicast protocols to complement the basic Trill protocol for additional functions that are to be supported. Trill never got evolved to that level. Such functions, such methods never got defined, never reached formal standardization stage. And that also to an extent restricted the further deployment, use, evolution of L2MP as a protocol. But the death knell for L2MP technologies in general, and the fact why no more focus was given to designing O&M, no more focus was given to use this Trill header to handle the tenant problem, because by then a new technology came in called the NVO3 technology, which actually put the final nail in the coffin for L2MP technology. Okay. While I say this, I'll say this with a pinch of salt. See, you will, if you go around searching around the world in what is being used in the data center networks across the globe, I am sure you will still be able to find some data center networks which are even today using virtual chassis technology. You will still find some data center networks, some part of the globe, which are even today using Trill and L2MP technology. Why? Because it solves their problem. They don't want to evolve. It works well for them. But the larger data center networks, like the ones which Facebook have, Amazon have, right? Those have evolved. They no longer use L2MP, they use NVO3 technology. Okay. So at this point in time, by this point in time, the network topologies, which was earlier. See, when I talked about STP, when I talked about virtual chassis, when I talked about L2MP, the underlying topology was still the access aggregation core topology. We were changing what in that topology? We were changing protocols, control plane, data plane, management plane protocols, coming up with new concepts like virtual chassis, L2MP. But the underlying structure of the network was with still access aggregation core. But access aggregation core, apart from all these challenges that we are talking associated with the technologies, virtual chassis, L2MP, they also have another fundamental problem which exists with the structure of the network. And what is that? The blast radius. Remember that we talked about? The blast radius of L2MP is very, of the access aggregation core structures is very high. Topologies is very high. Two, we said they are suited for client server traffic. Server traffic needs a lot of multiple paths through the network, not just the dual paths that we see in the access aggregation core topology. So as the applications evolved to cluster-based applications, by now people were also thinking we've had enough of this access aggregation core structure or topology. Clause or leaf spine topology is better suited for server kind of traffic. Okay. So when you see the modern data center networks, one is the evolution in the protocols, in the technology, moving from L2MP to NVO3, which I'm going to talk about next. The other is the structural or the topological change from access aggregation core to clause, leaf spine topology. That is the final step which we had discussed, the clause topology. But before reaching that final step, the technology which works with the clause network topology is the NVO3 technology. Okay. So in terms of the modern data centers, we've talked about the underlying topological structure, which we said is the leaf spine topology or its extension. But what are the protocols that run? Earlier, I just made a simple statement saying they all leaf and spine switches run L3 protocols. That's all I had said. In reality, the technology that is used is called a NVO3 technology, Network Virtualization Overlay Technology. Okay, it's an extension to L2MP. The thought process is the same as L2MP, but it's a step further. It goes all out while L2MP stopped a step in between. It continued because it was still driven by those access aggregation core mindsets. It stopped short of completely going to layer 3. It came to L2++. But NVO3, and because of the fact that NVO3 technologies realized that the underlying network topology was also going to migrate from access aggregation core to clause, they went all out and they said, we don't need L2 protocols anymore. I mean, when I say L2 protocols, of course, you need an entire protocol stack, but I don't need to base my switching function or routing function, forwarding function, tie it up with L2. That I don't need to do. So they went all out to say, okay, we will embrace layer 3 technology, the IP routing functions, IP technology at the heart of the clause network, the leaf spine network. And that is what NVO3 does. Okay, so just like L2MP is a tunneling technique. NVO3 is also a tunneling technique. The difference being it tunnels server traffic not through a trail network, but it tunnels it through a IP network. So whatever we talked about L2MP or trail, the concept, same concept holds true for NVO3. But the fundamental change is that it's not a L2++ protocol like Trill. Right? It's a complete layer 3 network, an IP-based network. All the switches, which we call as the leaf switches or the spines, these are leaves. And then you have the spines. They're all IP routers in reality. And that actually should also clarify, while I've been using the term switch and the literature also calls them leaf spine switches. You know why it's called switch? Because it's borrowed from the telephony architecture. In telephone, you call everything a switch, telephony switch. Because clause is a topology that's evolved from the telephony architecture, they still continue to call it a leaf-spine switch. But in reality, they are IP routers in the NVO3 world, in the modern data centers. So essentially, this is no longer a Trill network, it's an IP network. The leaf-spine switches are no longer L2 switches, they are layer 3 routers. And therefore, the physical servers, which are senders of data, right? If they want to send a L2 frame still, like they were doing earlier, the leaf switch can actually act as what we call as in NVO3 technology, NVE, a network virtualization encapsulation node. It can take this L2 frame, encapsulate it into a IP header and send it over the IP network. I can create, so this is typically like your VPN, setting up a VPN over the data center network. So it's a NVO3 is a tunneling technology. It's a layer 3 tunneling technology where you take any data coming from a server. That could be a layer 2 frame. It could even be a layer 3 IP packet. I don't care. We call it a, what do you call it? The term is, yeah, packet only, right? Datagram is at the transport layer. So if I'm creating multiple tenant networks over my modern data center network, my tenant may be the virtual machine of my tenant may be generating L2 frame, or the virtual machine of my tenant may be generating L3 packet, sending it towards another virtual machine. I don't care. My leaf nodes act as NVEs. They take the traffic generated by the sender, encapsulate it into an IP payload, create kind of a VPN tunnel, and send it towards the destination. This is NVO3 technology. Okay, so we have these leaf nodes are called NVEs in NVO3 technology. The name that is given to them, Network Virtualization Edge nodes. They encapsulate the sending traffic, whether L2 frames, L3 packets, encapsulate it, send it over an L3 network, which is the data center network, towards the destination. A new protocol has been created called the VXLAN protocol. So just like Trill reserved a 32-bit field, saying, okay, we will use this field later for tenant identification. NVO3 technologies also recommend that when you encapsulate a sender's frame into an IP packet, have some additional fields such that you can use them for tenant identification. Okay? And that has been done by creating a new protocol called VXLAN. It's an extension. It's not really an extension to VLAN. It's a different protocol altogether. But the reason for having VXLAN is the same. You want to support multiple virtual networks on top of the underlying data center network. Why? Because the data center supports multiple private VPCs of multiple different tenants. So you need virtual networks to be created. VLAN could do that, but limited by 4,000 tenants, the VLAN ID. So what is VXLAN doing? Okay, maybe I'll come to that in the next class. VXLAN is also doing something similar like Trill tried to do. It brings in a new network identifier called the VNI, which gets introduced during this encapsulation function that happens on the NVEs. This will become more clearer in the next class when I actually talk about VXLAN and how this VXLAN protocol handles the encapsulation. I'll next class talk about the encapsulation sequence, just like I showed you with Trill. You take a L2 frame and then you put it into a Trill header and then it goes over a underlying layer 2 network. I'll next class talk about how VXLAN encapsulation works. So think of VXLAN as a protocol that uses NVO3 as a technology similar to Trill that used L2MP as a technology. Both of them are tunneling technology. So that's what I want to spend a little bit more time today on. How do you differentiate between L2MP versus NVO3? to a very large extent, the way I've explained, they are very similar technologies. Because what are they doing? They're building tenant networks on top of the underlying physical network by using encapsulation or tunneling. I introduced this term earlier. These virtual networks that we create on top of the physical networks, we call them overlay networks, right? Because you have an underlay network, the physical networks is always called an underlay network. And what do you do? Remember that diagram I showed you when we talked about network virtualization? You are creating multiple virtual networks on top of this underlay network. VLAN did it by having a field VLAN ID. L2MP and NVO3, they do that by using encapsulation. They encapsulate the sending traffic into a newer protocol, and that new protocol has an additional field which identifies the tenant ID. L2MP protocols have in Trill have that reserved 32-bit field. NVO3 protocol like VXLAN has a new identifier called VNI, VXLAN network identifier. That is what is used instead of VLAN ID to identify a tenant network. So they both are building overlay networks on the physical network and using tunneling as a technique for carrying traffic through the underlay network. So if I have to send traffic in between an overlay network, what does that mean? That means, let me draw. This is my overlay network. This is my underlay network. So in my overlay network, I have a virtual machine and another virtual machine here. I want to create an overlay network. This is a tenant specific virtual network, and I want to see it like a layer 2 network. So if I want to see it like a layer 2 network, try to understand that this is very critical part of the entire discussion. What are these VMs? These VMs see themselves as layer 2 endpoints. So this VM will generate a L2 frame and send it on the overlay network, assuming that it will be switched and reach the destination VM. But in reality, this VM sits on a physical server in the underlay network. This VM sits on another physical server, and these two physical servers are connected via the Clos data center network, which is a layer 3 network. So how do I create an overlay network on top of an underlay network? I don't care what they are sending, whether it's an L2 frame or an L3 frame. Whatever they want to send, what do I treat it like? I treat it like data that has to be sent from one VM to another VM. I treat it like data. I take that data and I encapsulate it over the underlay network by creating a tunnel between these two physical servers. I just tunnel that traffic, and this physical server will detunnel it, give it to the VM. The VMs see the data coming to them, which could be the layer 2 frame. They feel as if it got switched through the overlay network and reached them. But in reality, that layer 2 frame never got switched through the overlay network. What happened? It got tunneled through the underlying layer 3 network and reached the destination. L2MP does the same. It tunnels it through the Trill network. NVO3 does the same. It tunnels it through a L3 network. VPNs actually do the same. They tunnel the traffic from your home to the enterprise through the internet, which is an L3 network. So tunneling is the underlying technology that is used in all of these NVO3, L2MP, VPNs. And tunneling works with encapsulation. Whatever has to be tunneled is treated as data. You encapsulate this data in next level headers and send it through the underlay network. So both technologies build overlay networks on top of the underlay physical network using tunneling technology. Where is the difference? The difference is that because L2MP is the L2++, they need to do more things. They need to have newer forwarding identifiers. They need to have newer switches called RBs. Whereas in contrast, because NVO3 technologies they just went all out and they said, we don't want to be stuck at L2++. We will just go ahead and reuse the IP forwarding and the IP suite of protocols. Our data center network, which follows Clos topology, is an L3 network. It's an IP network, like the internet. So they don't need any new logical network identifiers. They use the traditional IP addresses. They use the IP routers. Nothing different. It's like an IP network within a data center. Okay. So NVO3 are much more simpler compared to L2MP because they reuse everything that comes associated with IP. They are similar to L2MP because they are also creating overlay networks over underlay network using tunneling and encapsulation. But the way they benefit is because the underlying network is not L2++, it's actually a layer 3 network. So they get all the benefits of IP. They don't need new RBs. They can just go to market and procure these L3 switches or routers as leaf and spine nodes. So that's what we have modern day. So this is the evolutionary path I wanted to cover today. From year 2000 to today, what has changed? One, the topology has changed from access aggregation core to clause, but in between the technology has also evolved. The protocols have evolved, and that is the journey we saw today. Okay, so we are also out of time for a class. I'll stop here today. Next class, I'll talk about VXLAN protocol. We'll go deeper into NVO3 and how VXLAN works, and then how VXLAN is today the key protocol used in modern data centers. Right? No longer VLAN. And then I'll give you a lab for VXLAN. It'll help you better understand VXLAN protocol. By the way, some labs I posted, you may not have done it because of the midterm exam. The assignment is also ongoing. So focus on that, just check that, do those. I'll post the next VXLAN lab assignment after next week, after we've covered the protocol in class. No, Tanya, no specific guidelines on the assignment. It's not a very complex assignment either. Just make sure that the required snapshots that I've asked you when you do it in Wireshark, just take those snapshots, pictures, and include it in your report, because that's proof that you've done it. Okay, that's all. Other than that, nothing more. Okay, so I'll stop here. We'll continue this discussion next time on data center networks, and we'll now reach the protocol part of it, VXLAN. That's something we'll do next time. Thank you very much. See you next Sunday. Till then, bye-bye.